this problem solving session on simple harmonic motion, I will be solving 4 problems. One where a roller is attached to a spring and performs simple harmonic motion, and the other problems are concerned with phasor diagrams and energy and simple harmonic motion. So, for the first problem, this is from GATE 2011. The problem is like this: a disk of mass m is connected to a spring at its center and it is on a rough surface. Of mass m and radius r is connected to a spring of spring constant k. So, let me write it here. The spring constant is k. The mass of the disk is small m and the radius is r. It is performing simple harmonic motion while rolling without slipping. What is the frequency of this simple harmonic motion? So, let us see. First thing, we want to understand whether I would expect this frequency to be larger than if there was a point mass that was oscillating. So, let me make that picture. Suppose instead of this rolling disk, I had a block or a point mass of mass m and this being k. In that case, the frequency would have been square root of k by m, or the frequency would have been 1 over 2 pi square root of k by m. In this case, what do we expect? So, physically what we expect is, suppose this disk is displaced from the equilibrium position this way, so that the spring is stretched and the disk is out here. There will be a restoring force kx when it is displaced by x. At the same time, since it has a tendency to slip towards the left, there will be a frictional force to the right. In effect, what that frictional force does is that it reduces the amount of restoration force. Effectively, k is becoming smaller. If k is becoming smaller, the frequency should go down. That is a physics anticipation. Let us now solve it mathematically. So, when the disk is displaced by x, I am going to have m x double dot is equal to minus kx plus f, because you see the way we have made it, x is going to the right, kx force is to the left and frictional force is to the right when it has a tendency to come in. So, mx double dot is equal to minus kx plus f. At the same time, I have the rolling equation, that is I theta double dot is equal to f r. Now, we have to be careful in this case in fixing the directions. The way I have written it, the theta has a sense of going counterclockwise, right. That is how f r is going to give me that kind of torque that I have written. And when the disk is rotating counterclockwise, x dot, that is the velocity, if it is to roll, is going to be negative. So, the constraint of rolling gives me x dot is equal to minus r theta dot, or x double dot is equal to minus r theta double dot. So, I have these three equations now, and I can solve, eliminate for a frictional force F theta and get the equation for x double dot, and that will give me the oscillation frequency. So, we have these equations which I am going to write again is mx double dot is equal to minus kx plus f. Then I have I theta double dot is equal to fr, which I am going to change because I for a uniform disk is m r square by 2, theta double dot is going to be equal to fr, which gives mr theta double dot over 2 is equal to f. And the third equation is that x double dot is equal to minus r theta dot. This is my third equation, this is my second equation, and this is my first equation. Substitute third equation in 2 and we get m x double dot with a minus sign divided by 2 is equal to f. We substitute this in 1 and you get mx double dot is equal to minus kx minus mx double dot over 2, or 3 over 2 m x double dot equals minus kx, which gives me omega equals square root of 2 k over 3 m, or the frequency equals 1 over 2 pi square root of 2 k over 3 m. You see the frequency is less than square root k by m as we anticipated. Problem number 2. This problem concerns itself by with making phasor diagrams. So, simple harmonic motion by a particle has angular frequency omega equals 5 radians per second. If the initial condition for its motion is x at 0 is equal to 0.1 and x dot at 0 is equal to 0.15, and the motion is represented as x t equals a cosine of omega t plus phi, show the motion on a phasor diagram. So, if I look at the phasor picture, what do I do in this case? I make a vector which is rotating like this, and its projection on the x axis gives me a cosine of omega t, where a is the radius or the amplitude of the motion. In the present case, if I again make this circle, at t equal to 0, x is greater than 0 and x dot is also greater than 0. And keep in mind that this phasor is rotating counterclockwise. If I look at this quadrant, in this x is positive, but x dot is negative. So, let us write here x is greater than 0 and x dot is less than 0. How about this quadrant? In this quadrant, x is less than 0 and x dot is also less than 0. Here x is less than 0, x dot is greater than 0 because this arrow would be moving this way. And in this quadrant, which I will show by red, x is greater than 0 and x dot is greater than 0. So, if I have the initial conditions that x is greater than 0 and x dot is greater than 0, the phasor must be somewhere here. This is how it will be at t equal to 0 position, and then it rotates like this with angular frequency omega. So, initial phase is given here. You can see that initial phase is negative. Let us now do this mathematically. So, you are given x t equals a cosine of omega t plus phi, which gives me that 0.1 is equal to a cosine of phi. X dot t, which is equal to minus a omega sine of omega t plus phi, implies 0.15 is equal to minus a omega sine of phi. You can immediately see that this is my equation 1, equation 2. If I divide equation 2 by equation 1, I get minus omega tangent of phi equals 0.15 over 0.1, which is 1.5, and therefore, tangent phi is equal to 1.5 over 5 with a minus sign, which is minus 0.3, or phi is going to be approximately minus 0.3 radians. So, you can see this phi out here is coming out to be 0.3 radians on the negative side, and then on the phasor diagram, this is how I represent the motion. You can keep trying other such combinations. For example, if I give you that x is equal to 0.1 and x dot is equal to minus 0.1, in that case, on the phasor, if I want to represent the motion as cosine omega t plus phi, it will be initial position will be somewhere here, and then the phasor will be moving to the left. Similarly, if x is equal to minus 0.1 and x dot is equal to 0.2, then the phasor would be in the third quadrant and would be turning like this. And by our convention, since we restrict phi and from minus pi to pi, this will be phi negative out here. Finally, if I have x equals, let us say, minus 0.2 and x dot is equal to minus 0.2, then both are negative and the phasor would be somewhere here and rotating like this. All this has been done keeping in mind that x t is represented by a cosine of omega t plus phi. What if x t is to be written as a sine omega t plus phi? In that case, recall that for same phasor, its projection on the x axis gives me cosine and its projection on the y axis gives me sine. If I want to represent the motion as sine, the only difference that will come, and after that I will leave it for you to work it out, would be that if the phasor is here, the motion would be projected on the y axis, and for the first quadrant now I am going to have x greater than 0, because this is what x is representing, and phasor is moving up. So, it will be the point will be moving out. So, x dot would also be greater than 0. Notice in the cos case, the phasor initially was here if this was the condition. In the second quadrant, x would be greater than 0, but x dot will be less than 0 because this phasor is moving counterclockwise and this point would be coming down. Similarly, in the third quadrant here, if the phasor is made here, x would be less than 0, because now the phasor would be representing a point here and the point is moving down. So, x dot would also be less than 0, and in the fourth quadrant, which I will make with black, here x is less than 0, but x dot is greater than 0, because this point would be moving up. So, you can work that out for these conditions that I have stated. Next, I want to do a problem related with the energy of simple harmonic motion, and it is like this. A large hoop or you can say a large ring or a wheel kind of thing. So, there is a large hoop which is pivoted at its periphery, so of mass 2 kilogram and radius 1.5 meters is pivoted at a point on its periphery. So, this point is shown here, and this is a hoop. So, it is like a ring. All the mass is concentrated only on the perimeter, on the circumference. So, the entire mass is on the circumference, and this is performing, the hoop is performing simple harmonic motion with amplitude theta 0 if the average kinetic energy of motion is 0.3 joules. What is the value of theta 0? You can do this problem in several different ways, but I will explain different terms. So, now the solution. The average kinetic energy would be time average, which is 1 by t integration dt of the kinetic energy, which is 1/2 I about the pivot point theta dot square. And let us see what is this. Now, since this is performing simple harmonic motion, theta as a function of time would be given as, let us say it starts from the extreme. So, I am just writing some theta 0 amplitude cosine of omega t, and therefore, the time average kinetic energy, which I will show by these angular brackets, is going to be integral dt I over 2 theta 0 square cosine square omega t omega square. Now, for the average, instead of 1/2, this should be 1 over the time period t, 1 over the time period t. Now, 1 over time period t dt averaged over the time period comes out to be 1/2. So, this is going to be I by 4 omega square theta 0 square, and it is this quantity which is given to be 0.3 joules. So, all I have to do is calculate I, calculate omega, and then calculate theta naught. Now, for this hoop, I is going to be about this point. So, I about the pivot, which is given here, is going to be I cm plus m r square, which is going to be m r square plus m r square is 2 m r square. What about omega? That is the frequency of angular frequency of oscillations. So, if I displace this, let me make this in a different color. If I displace this hoop by an angle theta, the center of mass comes here, there is a force mg, and the restoring torque is going to be mg r theta with a minus sign, so that it shows that it is restoring. So, I am going to have I theta double dot is equal to minus mg r theta. This is 2 mr square theta double dot is equal to minus mg r theta. Let us cancel a few terms. M cancels, one of the r cancels, and therefore, I have theta double dot plus g over 2 r theta is equal to 0. So, omega is equal to square root of g over 2 r. Now, what do I have from the previous page is that the average kinetic energy is 1 over 4 I omega square theta 0 square, which is given to be 0.3. I is 2 times m, which is given to be 2 kilograms, r square, which is given to be 1.5. So, this is going to be 2.25 divided by 4. Omega square is going to be g over 2 r, g is given to be 10 over 2 times r is going to be 1.5, theta 0 square is equal to 0.3. So, this gives me theta 0. Let us cancel a few terms. 1.5 goes with this and gives me 1.5. 2 goes with this 4. This 2 goes with this 5. So, I get theta 0 square is equal to 0.3 over 5 times 1.5. This 0.3 gives me 5 again. So, 1 over 5 or theta 0 is equal to 1 over 5 radians, which is 0.2 radians, and that is the answer. Finally, the fourth problem is taken from a paper in American Journal of Physics. It is based on some experiments that were shown there, and the problem is like this. There is a spring block system. However, this block now is going to be an empty box in which we put sand, and as this performs simple harmonic motion, the sand starts leaking. What happens when the sand starts leaking? As the sand starts leaking, the energy is going to dissipate with the sand, and therefore, the amplitude should go down, and that is a problem. So, let me now write the problem. A spring, so we want to find that amplitude as a function of time, and that is the problem. Spring mass system is made of a spring of spring constant K and connected to empty box. The box is filled with sand, so that the box plus sand have mass m0. When the system is oscillating, the sand starts leaking slowly from the box. with negligible relative velocity with respect to the box. What that statement means is that the velocity of sand which is falling or leaking is the same as the velocity of the box at that time with negligible relative velocity with respect to the box. Find the change in the amplitude as a function of time if the rate of leakage dm dt is equal to minus c, c is a constant, if the initial amplitude was a0. Assume t oscillation, that is time period, is much less than m0 over c. That condition is important. That means the leakage rate is so small that for a few periods we can take the oscillation period to be roughly a constant. So, it changes over a longer period of time. So, let us see what is happening. As this spring mass system is oscillating, the sand is leaking out and the rate of sand coming out is dm by dt is equal to minus c, where c is a constant. As the sand comes out, it takes away energy from it. So, energy leaking out in time delta t is going to be equal to delta m over delta t x dot t square, where x is the velocity at that time, 1 over 2, that is it. So, if delta m by delta t is negative, energy would be leaking out, it will come out with a negative sign. In time delta t, it is going to be times delta t, and therefore, rate of energy leaking out is going to be equal to 1/2 dm by dt x dot t square, which is nothing but 1 minus 1/2 c x dot t square. And since we have already assumed that t oscillation is much less than m naught over c. So, mass does not really change much during an oscillation, and therefore, I can assume 3, 4, 5, 10 oscillations there is a angular frequency and there is an amplitude, and therefore, I can write this as minus 1/2 c omega t. Omega is going to be a function of time because mass is changing with a function of time, but although very slowly. Omega square a square t square cosine of square omega t plus phi, which is a phase, but I am taking that to be 0 without any loss of generality. So, this is going to be the rate of energy leaking out. So, let me write this equation in a different color. dE dt, the rate at which energy is going out at any time t, is minus 1/2 c omega square t a square t cosine square of omega t, which I can further write as minus 1/2 c k divided by m naught minus c t a square t cosine square omega t. This is my equation for loss of energy at any given time. Let me write this again. So, I have energy loss is equal to minus a half C k over m naught minus C t a square t cosine square omega t. So, average energy loss per cycle is going to be equal to time average of this whole thing minus a half C k over m naught minus C t a square t cosine square omega t time averaged. And as I said earlier, because C is very small, change in A is very small, I can think of per cycle they are not really changing much. So, I will take time average of this quantity only, average. And what is the average of this quantity? This is 1/2 over a period. So, average energy loss per cycle is minus a quarter C k over m naught minus C t a square t. That is dE dt time average. These angular brackets represent time average. So, we found the change in the loss of the energy, and I can now make differential equation for change in amplitude through this. How do I do that? Keep in mind that the energy at any time is, total energy is k A t square, and if I take its d by dt, this is equal to dE dt time average. And therefore, I can write this differential gives me k A dA dt, which is equal to minus 1/4 C k over m naught minus C t a square t. I can cut a few terms on the two sides. So, this a cancels this square, and therefore, and this k cancels this k, and therefore, I get dA by dt is equal to minus 1/4 C over m naught minus C t a. This is the differential equation for the change in the amplitude. Keep in mind again that the leakage rate is very small, and therefore, we have dA over A is equal to minus 1/4 C dt over m naught minus C t. I can integrate this from A0 to A in time t equal to 0, so some time t, I will make this prime. So, this becomes log of A t over A0 is equal to minus 1/4 C divided by minus C log of m0 minus C t prime t equal to 0 to t. So, this is 1/4 log of m0 minus C t divided by m0. This immediately gives me amplitude as a function of time equals A naught times 1 minus C t over m0 raised to 1/4. You can see as time progresses, the amplitude keeps going down.